Hi everybody, Dr. White here with a little tutorial on using R to do computations involving normal distributions. So let's log into RStudio. Okay, it's happening. Alrighty. Got a file here I'm not using anymore. I got some unsaved changes in it. I'll go ahead and save my changes, close it out. I'll clear out my global environment. And hey, let's just go ahead and restart R, just starting off from 0, contributed packages attached. So we're all in the same place. Let's go get some material for today, /com. Dr. White stuff, Math 331. And under scripts, there's a section Ch03-3.r, which I will save right into my home directory. In fact, I'll go right to my notes folder. You can do that right away. /my notes after the twiddles, say OK, and then you're looking straight into the My Notes folder and you can save there. Alrighty. So I'm going to make this a bit bigger for you. So how do we compute with normal random variables? Let's say that X is normally distributed with a mean of 70, okay, and a variance sigma squared of 9. If you needed the height of density curves at any point on the x-axis, like say where x is 71, then you can use the d norm member of the norm family of functions and just put in your x value. And you've got to say what the mu and the sigma squared are, but the way that R takes them, it takes the mu and calls it mean, and it doesn't take the variance, it takes the standard deviation. And so you have to remember that when you switch back and forth between R and the textbook. So you're going to have to say mean is 70, but more importantly, remember SD, for standard deviation, is square root of 9, 3. And then you'll get that particular height above the curve. Now, much more likely, you're going to want to know probabilities for the curve, which is like, integrals of the PDF. And so the cumulative distribution function is where you want to go. Like, what is the chance that X is no more than 74? No, that should be a 73, I would think. That chance would be the P norm, and you put your upper bound, and you're going to get the probability that it's less than or equal to 73. You say the mean, you say the standard deviation. You don't have to name them if they're in the right order. So about 84% chance. What's the chance that X comes within 1 standard deviation of its expected value? Well, one way to handle that is to take the chance of coming less than expected value plus standard deviation and subtract off the chance of coming less than expected value minus the standard deviation. And so that difference would be your answer. Notice it's about 68%. Remember how we said that for a lot of random variables, it's a rough rule of thumb that there's about a 68% chance they're going to come within a standard deviation of their expected value. That's actually because a lot of random variables have distributions that are approximately bell-shaped, like the normal curve. And the 68% figure comes from the normal curve. 68% chance of coming within 1 mean of your standard, of your expected, with 68% chance of coming in within 1 standard deviation of your expected value if you're a normal random variable. If you need quantiles, if you need percentiles, then they're called quantiles in our world. And so there's Q norm. All you do is you put your desired percentile, like say if you need the 3rd quartile, the 75th percentile, put in 0.75 as a decimal, and then specify your mean and your SD, and off you go. So in order to be, like say if this was a population of people where the mean height was 70 inches and the standard deviation of the heights is 3 inches, in order to be at the 75th percentile, to have 75% of people shorter than you, you would need to be that tall, 72 inches roughly. You can also simulate normal random values with R norm. So here, I'm using R norm to get 10,000 tries of a normal distribution where the mean is 70 and the standard deviation is 3. And that's a lot, so I'm going to store the result in a vector called sims. So I'll run this, and I got sims in my global environment, as you can see. And I'm going to go ahead and make a data frame out of that where the only column is the simulations. So click on it, and yeah, look at those numbers. You know, they're all kind of like around 70, give or take some. And let's go ahead and plot those 10,000 values. Let's make a density plot for those 10,000 values. And remember, a density plot is some attempt to estimate what the PDF would look like if you could somehow know the distribution exactly, but all you have is this data from the distribution. So we'll load ggplot2 so we can make these kind of graphs, and we'll make this density plot and have a look at it here. So I'm going to remove my face. And sure enough, it looks like a bell-shaped curve, you know, centered around 70, and it even looks like the inflection points could be back at 67 and up at 73. Pretty neat. If you want to see graphs of your PDF with shaded areas underneath them representing probabilities when you do probability calculations, then you might be interested in pnorm-GC. So that's in the TigerStats package, so I'm just going to go ahead and get that loaded up. And here's how it works. Like, say you want the probability of coming within 1 standard deviation of your expected value, the chance that X is between 67 and 73. Then you call up pnorm-GC, and you have to feed it the boundary values. They're stuck together with the C function here in R to make a little vector of length 2. And you got to say that you want the chance of coming in between them. So you say region is between. And then you can specify your mean and your standard deviation. And if you want to see more than just a numerical answer, say graph is true. And run it. And here's your 68%, just like with the previous computations using the regular pnorm. But over here, you see that this shaded blue area here represents the 68% chance. If you wanted the chance of being less than 67 or more than 73, then you could say region is outside. Just saying. If you want to work with percentiles, there's qnorm-GC. So like if you needed the first quartile of this distribution we've been working with, you enter 0.25. Now you need to say region is below, and then mean and standard deviation. And it'll give you the answer here. So you need to be about 68 inches tall in order to be taller than 25% of the people exactly. And over here, where you want the 25th percentile, they're saying the 25th percentile is this 67.98. This shaded area here is 0.25. So that can be helpful a little bit. If you want a little more detail on how to use pnorm-GC, just ask for help GC, pnorm-GC. You'll pop up a web page. And qnorm-GC, I believe, also has some special help. Yeah, it does too. So there we are. And guess that's all that we want to do. I'm going to go ahead and set this back just because I don't want to confuse myself about the problem versus what the code was here. Save my results. And maybe I'll clean up my global environment now. And maybe I'll restart R. But eventually I've got to log out and say goodbye for now.